Okay, well, one thing I haven't talked about is dispersion. You can see here, obviously, they're not all the same value in the middle. They're dispersed about, and I've already talked about it being skewed and having a long tail. Those comments are about the overall distribution and dispersion or variability of the distribution or the variable. And we could talk about those things too. So there are various ways of measuring how dispersed or how variable something is across its range. Some of them might be kind of all bunched together, very little range. Others might be a huge range. And of course, in the case of salaries, there's an enormous range of salaries from naught up to, tens of thousands of pounds in the end. The simplest way of talking about this is to talk about the range. So the range of values, and its simple concept, is the difference between the highest and the small and the largest. Sorry, the highest and the smallest and the biggest. The two extremes at either end. So going back to the Facebook users, here's the same set of 11 numbers. The range is the biggest one, 252, minus the smallest one, 22, 230. Very simple figure. Trouble with this is, it's a very intuitive kind of concept, but it's very biased by outliers. The fact that there is that one person there who's clearly very popular, who has 252 friends on Facebook, is pushing up the range to a much higher figure than it would otherwise be. As you can see, if you're just looking at the numbers, you can see that most of them bunching around the 90s and the hundreds and so on. So, a field where the middle is very, very distant from the range. The range is twice the mean, you might say, in this case. The mean, remember, was 96.64. So the range is not a very helpful figure at all. Intuitive, but not very helpful. But there are other measures of range that are slightly more helpful, and these are things called quartiles. Quartiles divide up the range of things into 4 groupings. And it's basically the idea of the median repeated again. So the median, remember, divides out the distribution into 2 halves, 2 equal numbers, half having values below, half having values above. Well, we do that again, and we get quartiles. So the lower half, the 50% of people who fall below the median, we can split them again, so we have a quarter in the bottom group, a quarter in the next group along, and then we can do the quarter in the third group and the quarter in the fourth group. So effectively we're taking medians of the two halves either side. So we effectively split the entire population, the number of people we've got in the population or the sample, into 4 equal groups, 25%, 25%, 25%, and we say what the values are that split them up. The lowest 25 goes up to a certain value, and that's called the lower quartile. And then it goes up to another value, that's the median, then it's the upper quartile, and then finally, of course, the maximum value. So going back to our friends thing, sorry, this is slightly, I hope you can see that. It's in the red and the blue colours don't come out terribly well, but again, we've got the same numbers again in order. We have to do it in order because with medians and quartiles we have to sort them into order. We've got the median the same as before, 98 in the middle. So that's the 98 here. And then we do the same for the 5 this side. The middle one is number 3, and that's a value of 53. And going the other way, you've got 116 as the upper quartile. Very small numbers this, so it begins to get a bit uninteresting. But what you're saying is that the interquartile range, that is the half of the people who are in that middle group, who are, so have a quarter below and a quarter above, but the half remaining, are between 53 and 116. Now we begin to get a better idea of where that middle range is now. It's not as it's not as skewed as the range was. Remember, the range was 230. It didn't help at all. But now saying we have an interquartile ratio of 53 to 116 gives us a bit more idea of where that middle group is. And in fact, this is used on another one of the charts that Tukey produced, the Boxplot, and it can be a useful way of showing a distribution in this way. This is what a box plot looks like. They're normally plotted upwards rather than horizontally. So the distribution starts with the lowest value down here and goes up to the highest value up here. Here's that range. The chart itself I produced in SPSS, so you can do this in SPSS. There's a box in the middle which is arbitrary width. The width is just so you can see it, but it doesn't really matter. That width is arbitrary. But what is important is that height there and where that line in the middle is. This line here indicates the median of this distribution. So, as I said, the median is the one that has half of the points above and half the points below. So we can see the median was here. I don't know what that was. What's his age, isn't it? So it'd be 21, I should think, as the median value. And you can see you've got, in this box, that's the interquartile range. So we've got a quarter of the people lying in this range here, between 21 and, must be 26. And we've also got a quarter of the people lying in this box here, which is 21 down to 20 by the looks of it. And what you can begin to see very, very quickly, just by looking at that chart, is you can see it's skewed, that it's not even, it's not distributed evenly. The median is quite near the bottom end of the range, and in fact, a large number of people are squashed in to these low values here, 20, 19 and 20. So we can see we've got a skewed distribution because the median is not in the middle of the box here. The second thing it shows is the further distributions at either extreme. And that's what these things here called, these T-shapes, called whiskers actually, and the upside down one there, are showing you where further values come. And in fact, I think in SPSS it's something like 90% of the interquartile range. So the interquartile range, of course, would be everybody else. So 90% of that gives us 90% of the people coming up to there. So within that range there to there, I think there are 90% of the interquartile range. And again, down here, you've got the same 90%. Again, you can see that it's going to be, it's skewed again. But at the bottom end of the range, we're packing them into just a small, these are the 19-year-olds down here. We're packing them into just a small range. Here we've got a much wider range of people. So the higher ages are shown by that longer whisker at the top. So you get a very quick visual feeling for the fact that the chart is, or the distribution is skewed to the lower end of the range. There are one or two other things on the chart. There are these 2 points here. There's this one labelled 25 and this one labelled 13. By the way, these are the case numbers, not the ages. That one's actually aged, what is it, about 36. And that one, I think, is 53. That's their actual ages. But they're just case numbers. And they're called outliers. They're the extreme ones. They fall outside that 90% range, and they give you some indication. They can be used, going back to the lecture a couple of weeks ago, they can be used to check your data. Can you have someone as old as that in this group? Well, actually you could. There was a 53-year-old in that particular class. But you think very carefully about it. Come on, can we really have somebody that old in the class? Is that likely? And you might want to go back and check that it is a true number. So outliers can be used as a way of data checking, but also a way of feeling just how extreme the cases can be. Okay, so that's what a box plot does, a useful mechanism for giving you a visual feeling for what the distribution looks like. In this case, we can say it's a skewed distribution, and we've got some outliers at the top end of the scale. And we can see roughly where the bulk of people are in that age range between, 21 and 26. Similar things shown by the histogram, where the bar indicates the frequency. This is of the age, again, the same actually distribution of that age of the health and illness students. I've shown the same figures using a bar chart. It shows similar things, but you have to interpret it in a slightly different fashion. Again, you can see the skew. The skew is to the lower end, down at the lower ages, 19, 20, 21, are where most people are. So the height of this is showing how many in that range. And then there are relatively few. There are some slightly older, mature students here, and then there's one real kind of outlier on the range there. So again, you get the feel for a skewed distribution. Doesn't give you quite the detail of the outliers and things like that of the box plot, but nevertheless, it's a commonly used chart, and it shows us, again, gives us a feel for what that data look like. Okay, well, we can also measure variability as well. As well as looking at it, we can calculate range and interquartile ratios, but we can measure it in other ways as well. We can actually create or calculate numbers which show us the variability of a variable. So going back to this chart here, how much does it vary? How much does that age vary across this population? For some it might be little variation, for others it might be a very large variation across the population. And that's what the notions of variance and standard deviation are doing. They're trying to get a calculation of a number that indicates just how much variation there is. We start that calculation by doing a sum of each individual's variation from the mean. So the beginning calculation for our standard deviation is to calculate the mean. So let's say we've got these scores here, 1, a 2, a 3, another 3 and a 4. Very, very simple example of this. Then the mean is 2.6, so we've added all those together and divided by 5, we get 2.6. And the deviation from, so that minus the mean is minus 1.6. 2 minus 2.6, minus 0.6. 3 minus 2.6, 0.4, and so on. Very simple calculation. Of course, if we add up all those deviations, we get 0. The overall deviation from the mean is by definition 0, because that's what we calculated to be. So it's not very helpful, that. So what we tend to do is square the numbers. We square those deviations to get rid of the sign, basically, a simple mathematical fiddle, if you like, to get rid of the signs. We just square it. So we take the minus 1.6 and square it and get 2.56. We take minus 0.6 and square it and get 0.36. Now when we add them up, we've got a number that's giving us some indication of how much variability there is. The more things vary from the mean, the bigger that number will be, that 5.20. The sum of squares it's called. Unfortunately, of course, the more people we have, the bigger that number will be as well. So we have to divide by the number of people we got to even out the size of the sample. So to get the variance that we want, we divide by, in this case, 5 individuals. So 5.20 divided by 5 gives us 1.04. That's the variance. You'll see that used a lot. In lots of statistical tests, you'll see the variance mentioned. And it appears on lots of tables and printouts. So the variance is a measure of how much variability. The higher the variance, the more variability, other things being equal. And of course, we've taken into account already how many individuals there are. So even if the sample size is double that or treble that, it still measures the amount of variability within that sample by comparison. Now, originally I said we square the numbers because we're going to get rid of the sign. Well, mathematicians realise that and realise the variance is a rather large number because it's squared. So what they often do is take the square root of it, and that gives you the standard deviation. Again, mentioned in lots of statistical outputs. The standard deviation is probably the standard measure of variability across samples. So we take 5.2 divided by 5 and the square root of that to get 1.02. Again, you won't need to do these calculations. That's why we have a stats package. It will do it for you. But it's useful to know where it's coming from, and it's useful to know what it's measuring. In this case, it's measuring how much things vary from the mean. So we've calculated the mean, and we've said some things are above it, some things are below it. How much are they varying? Are they varying lots or a little? So the lower the value of the standard deviation, the less they vary. The more they're clustered in around the mean. And the bigger the standard deviation, the more they're spread out. The flatter the distribution is, if you like, the more they are at extreme values by comparison with the mean. Just to give you some idea, another way, I hope this is clear, another way of demonstrating these differences. I've got two charts here, the left-hand chart and the right-hand chart. Both have the same mean. So there are different individuals. Each of these dots is an individual. I think, what's this measuring? Overall rating of a lecturer. So obviously someone has some lecturers rated. And here's lecturer number 1 rated at 3. Lecturer number 2 is rated at 2 by the looks of it. Lecturer number 3 is rated at 3 again. Another one at 3. And this one here rated at 2. A different set of lecturers are rated over here, same number of them. They have the same mean overall. The mean rating is just here, 2.6 or something, 2.6 it must be there. And it's the same here. But what we've got in the second diagram is much more variability. This lecturer is rated at 4, that one at 1, that one at 5, that one at 1, and so on. So we've got two situations, two different groups of individuals having the same mean, the same average value if you like, but having different amounts of variability. On the right hand side you've got a lot of variability, some scores are very high, some scores are very low. In the first case they're all bunching around the mean much more. So we've got very little variability in this. So low standard deviation, high standard deviation in the right hand side. And that's not uncommon in distributions. We do find distributions might share the mean value, or perhaps even the median, but actually they differ in how much variability there is. And that's an important thing to know about, particularly for certain statistical tests. Okay, how do we get all these things? How's my time going? Yeah. How do we get all these things? Well, we go through SPSS and use the Analyze, Descriptives, Explore menu. Now again, I hope by now you've had a time to play with some of these things. You know where these things are. Analyze menu you'll use a lot. Go down a couple to the Descriptive, then there's a sub menu for Explore. And that enables you to calculate for any of the variables you've got in your data set, the mean, the median, the standard deviation. By the way, that's often abbreviated as SD, standard deviation. The variance, which is of course the square of the standard deviation. The minimum, maximum, which may be useful but often aren't. The range, again, dubious but sometimes useful. And skew and kurtosis. Skew I've already talked about. Skew is off to one side or the other. Kurtosis is about how big those extremes are. And you can also produce stem and leaf and histograms from that menu. So that's the Explore item in the Analyze menu. The other thing to do is to produce charts, and there are two ways of doing this in SPSS, using the chart builder from the graph menu, or what I tend to do is use the legacy menu, because you can pick particular charts straight off on that. You can say I want a histogram, I want a pie chart or whatever. I just prefer that way of doing it. You have to tell it which variables to work off, obviously for whatever chart you want to do, and then you can edit the chart once you've done that. So when you get a chart up on screen, I hope you've done this by now, because that was the first exercise last week. You've actually got a chart up on screen. Well, if you double click it, then you can edit it. And you can do various things to it. Let me just show you some of those things. You can, for example, here's a histogram. This is the bank data, I think, you worked with last week. You can change the colour. In this case, I've changed it from a coloured chart to a black and white pattern. That's sometimes useful if you don't have a colour printer and you want to print things out in black and white. It's useful to have something that prints well in black and white. So you can do that in the chart editor. You can also change what's called the bin size. And these two things are the same distribution, the same numbers underlying it, but SPSS is showing the bar chart in two different ways. And what it's doing is it's changing the width of the columns, and that's called the bin size. So in this one, they're quite wide bins, so the range of salaries goes from, what's that, about $5,000 to $10,000 a year, presumably. So there's a $5,000 a year width. In this chart, the same figures, but the bins are narrower. The bins now are just, I think, must be $1,000 widths. So that's $1,000, another $1,000, and so on, in difference of salaries. We get a finer grained picture, sometimes helpful to see that, sometimes not. So it's a matter of judgment on your part, what shows things the best way. You can change that bin size. If you want to show more variability, you can see that there are gaps here. There's obviously some salary range here where there are hardly any people that didn't show on the previous diagram. That may be of interest, it may not. It depends what you're trying to do with the figures. So you can play around with that to show the figures in the best possible way. Notice I've left this one in colour, by the way. You can also choose pie charts using the same menu. You can go through the legacy and pick pie charts and choose your variable, or do it through the single chart explorer. I've given this one, well, a couple of things to show here. I've given a shadow to it. That's a nice extra, but it's not that important. Shadows don't really help that much. But one thing I have done is split off the big group. That's what is this? This is employment category in your bank data. The clerical, that was most people. You can see immediately that the red group is almost half the sample were in the clerical grade. So it gives you a very quick idea of what's going on in the clerical in the employment categories here. And you can move it off to one side just to emphasise that a bit. Then you've got the blue group, and about another, just over a quarter office trainees. And then you get the idea, of course, that all the rest of the employment categories account for probably less than a quarter of all the staff working in this bank. So most of the staff were either clerical or office trainees. And it's a pretty clear indication of that from that pie chart. Okay, here's a box plot produced in SPSS. This again is that same data, the bank data. And I've just shown you this to show you two things. One is a much larger data set. We've got several hundred individuals in this sample now, rather than just, 34 I had before. And I'm showing one box plot beside another. You can do that to show different distributions. And what I want to show here is the distribution of, in this case, salaries for males and females working in this bank. Remember, this is American data for a particular bank. It's not showing you the data for everybody in the UK. It's showing you for an American bank for that particular employer. But one thing you can see very quickly, I think, by looking at the box plots here, is that the range, the variability of the male salaries is much, much greater than the variability of the female salaries. And you can see that in a variety of ways. First of all, remember, this is the interquartile range. So that's the median, and that's 1/4 and 1/4 below individuals. So this is half of all the men in this group here, in that range, is bigger than the female range. So the range of salaries for women in this bank was much, much smaller. You can also see that the outliers, the whisker up here for the men and all the outliers going up here, lots of them up here, very high salaries, relatively smaller for the women. Again, there were some outliers, but they're squashed down, a much tighter range of individuals. And you can see, of course, that the top values here for the women are much lower than the top values for the men. So at the top end of the range, men were getting paid more than the women. So that's what a box plot enables you to see. I mean, whether we like it or not, that's how it was, and we might be disgusted by that difference, but you can see it very clearly on this chart to see what that difference really is, and then talk about it. Okay, let me just finish by talking about the normal distribution. This is one particular distribution which I haven't really mentioned, but you've seen one or two diagrams showing it. It's the so-called bell-shaped distribution, and it's symmetrical. In other words, the top half and the bottom half are similar, and it's centred around the middle. So it's symmetrical about the centre. Sometimes also called the Gaussian distribution, named after the mathematician Gauss, who first developed the equation for it. And this is what it looks like. And again, you may well be familiar with this. I'm sure you've seen it. In popular literature, the bell curve is mentioned a lot as a way of talking about distributions of things. I've given you two examples here. There's the actual histogram, the blue thing, so with these values on it. And then the red line is showing you the perfect curve. If you kind of average things over very large numbers, that's what you get. You get the red curve, and hence the bell shape of it. Now notice it's symmetrical. So here's the mean value through the middle here, and it's symmetrical either side. It's not skewed to one side or the other, as were the data for salary. They were very skewed. They're not normal distributed. This is symmetrical. And notice that typically you get the bulk of people in the middle of the range here. This is where the highest frequencies are, and relatively low frequencies, very small numbers of individuals at either end, at the extremes here, the bottom end and the top end. A typical normal distribution. Now this is important because a lot of the stats that we use depend upon the fact that the variables are normally distributed. And I'll come back to this in later weeks, but we have often to check to see whether the data, the variables you're using, are like this, in which case you can use certain statistical tests, or if they're not like that, you have to use other different tests on them. So some tests are quite susceptible to the distribution not being normally distributed. So we have to check and see whether this is the case. Let's give you some examples. What's normally distributed? Well, people's height is normally distributed. Their IQ, measured by the IQ test, is. The number of hours they spend viewing TV, that's normally distributed. Blood pressure is normally distributed. Here's just one example of that, the blood pressure. So here's again that same bell shape. It's not quite as tall, this one's a bit more flat, but it's still got that same shape to it, the curve and the bulk in the middle, and then the same range either side. Not quite equal, slightly higher ones here than there are at the top end, but good enough for our purposes, a normally distributed variable. If you're worried about your blood pressure, by the way, if it's above that value there, then it's said to be hypertensive, high blood pressure. That's what the black means. Below that is not hypertensive. It's, what's the word for it? Normotensive. Oh well, there we are. So that's a typical example. And lots and lots of variables like this in both in kind of biology and in sociology, psychology, social measures of various kinds. A lot of things come out like this as normal distributions. What is not normally distributed, things to watch out for here? Well, income, we've seen that already. That income chart I showed you was very heavily skewed towards the low end with a long tail at the right end. Not a normal distribution. So many low earners, just a few earning banker salaries at the high end, you might say. So it's a skewed distribution and it's not normally distributed. Has the same kind of shape, but it's off to one side. Family size in the UK, that's also not normally distributed. Most families have 1 or 2 children. It's heavily skewed towards the low end. Some have no children, most probably have 1 or 2. And just a few families of the extremes have much larger numbers, up to 10, dozen, whatever. Very small numbers of families, though, in that kind of size. So it's a very skewed distribution. I'm just sorry, you've seen that. I've done that enough times now. That's the income distribution before. You can see it's skewed to one side. Now those terms, skew and kurtosis, I've mentioned before. Here's just to show you some diagrams of what they look like. The skew is a measure of how symmetric the distribution is. So if it's pushed to one side, it's skewed. If it's nicely balanced in the middle, it's not skewed. And we talk about positive skew, bunching at the low values on the left-hand side, and negative skew bunching towards the higher values at the right-hand side. And then the other term I mentioned very briefly is kurtosis, is the heaviness of the tails, how fat are the tails or how slim are they by comparison. I think I've got a diagram to show that. Well, that's skew, so I've said that already. So this one looks like the income one. It's a skewed one down to the low end. That's the other form of skew at the high end. And this is kurtosis. So both of these have roughly a symmetric shape with most people in the middle, but this one has very, very kind of slim extremes down here, and this one has quite fat extremes. So in other words, or lots of individuals down at the extremes. So it's a flatter kind of thing, and that's called kurtosis. Again, I think this would be an example. If I saw that in my distribution, I'd begin to worry about it. I think, well, what's going on here? It's a very strange distribution. What's happening?